Hello, welcome to another Stat 432 video. This is part 4 of or I guess my walkthrough of the UCI heart disease dataset analysis. So, picking up sort of where we left off, if I remember right, the very last thing we did was we sort of took our training data, removed any NAs, then we estimation, validation, split the data, fit a model, and sort of checked how we did when predicting the response, which again is this variable here with these possible levels. Okay, and we sort of have a bunch of to-dos here. So the big one I want to tackle in this video is setting ourselves up to be able to do cross-validation quickly and easily. I think that's going to be my only goal in this video, which will introduce sort of a new technology for doing this. And then in future videos, we'll sort of work backwards through some of these. We may do some of this in this video just for fun. But yeah, okay, let's do that. Let's do exactly that, actually. Okay, so I believe we need to run this code here. I'm going to run it sort of line by line just to make sure I know what's happening, to remind myself. And I'm starting from a fresh environment here because I think that's a good idea. Again, unless you have like unless you have like a model that took a long time to run, maybe it's better to restore. But for now, I want to work with a blank slate. Okay, so loading some packages. Right, okay, I'll read in the data. It looks like that. Okay, that's the full data. So here we are, test train splitting the data. I want to make note of something here. Actually, let's take some notes on this. In terms of here, let's call this ML pipeline. Okay, so what are the things that we always do when we're, let's say, training a machine learning algorithm, right? So read in the data. We did that. The next thing we do is test, train, split the data. We did that here. Let's run it. Okay, so now we've done that. The next thing we do. So I don't know where I want to put this yet, but so here we're sort of making the data be encoded the way we want. Here I was dealing with some issues with sort of hidden NAs. And then we saw that there were these 3 variables with a lot of NAs and we were going to remove them. We looked at the data, plot the data, fit a model. We don't need to look at this here anymore. Okay. I guess without getting into details, so test, train, split the data. But then the big next step is cross-validate within training data to evaluate many models. And to do more stuff here. So for now, and in this video for the most part, I want to just limit our discussion of cross-validation to fit a model. Oh, wow, it just really started raining. Anyway, split up the data, fit a model, make predictions, evaluate, do that thing like 5-10 times, right? Eventually, I'm going to circle back and say, like, within cross-validation, you should be doing some of the things like dealing with missing data, transforming variables, and doing things like that. But for now, we're just going to be like, well, within cross-validation, it does a bunch of data splits. It fits a bunch of models. It averages the results, and we can use that to pick a model. That's what we're going to focus on here. And in Stat 432, The next step is to refit chosen model to entire training data. And the last step is make predictions on test data. Yeah. Okay. So we're gonna operate here, and we're going to note that. Or no, sorry. What I want to say is these are really common things that you're always going to do. So people that are smarter than us, or more efficient than us, or more useful than us, I don't want to put people above us. But anyway, smart people have realized this. They're like, oh, we always do these same things over and over again. So why repeat ourselves? So in this class, you wrote a bunch of code to do cross-validation sort of from scratch, sort of. And hopefully you learned what cross-validation is from doing that. But in the real world, depending on sort of how deep into research versus like using things practically you are, you probably don't want to have to do that each time. So you want to deal with a pipeline. There's kind of a growing number of ways to do this in R. I think I mentioned previously, let's call it ML systems in R. So there's the carrot package. There is what I'll call the tidy models approach. There's something called MLR3. There's something I think it's called H2O. I think it's like that. I'm probably forgetting some. But all these things are different systems for sort of repeatedly doing these steps. I'm going to focus on this one, at least in this analysis. Maybe so I'm not as familiar with these. Maybe in one of the future analyses, I'll sort of step outside of my comfort zone and try one of these, and you can see me fumble with it and learn something on the fly. I'm particularly interested in this one here. But yeah, I'm going to start introducing ourselves to Carrot in this video. We've been using it all over the place, but now we're really going to dive into it. Okay, so I'm going to steal this code. So for this video, we're going to continue to work with this data here, which has all the manipulations you just saw me do, plus it removed any row with missing data. So really, we're going to be building up our pipeline here, but we still need to consider coming back and dealing with the missing data. And the other thing that I think we had a strong note on was this idea of maybe moving to a binary response instead of a 5-category response. I'm going to save that for later. I just want to build up this pipeline inside of Carrot. Okay, so let's set a goal here. So what do we want to do? I want to, with cross-validation, tune a decision tree, maybe k-nearest neighbors, and let's get wild, some form of boosted model. I don't know which one yet. We'll just pick one. We haven't learned this, but the point of this is to say that even though we don't know how this works, we can still evaluate it. That's kind of a thing I feel is very important. Okay, so I should note that we've already loaded Carrot, and we've already done the read and data step, which Carrot doesn't really help us with, but it's part of the pipeline in my opinion. But then the test train splitting, and we use this function to help with that, which is part of Carrot. Okay, so now we have our training data, which is here. And so far, when we've done modeling, we've seen all these different functions for doing it, right? So there's the GLM function. There's the rpart function from the rpart package. There was the knn3 function, which is from Carrot. There's this GBM function that we're gonna maybe look at some point. And so the point here is that there's all these different functions for fitting all these different models, and they all work differently. Worse yet, I think you'll all agree with me when I say if you call predict on any of the objects from these models, that behaves differently too. It's always different. Is it type class? Is it type prob? What do I need to return? What does it return by default? And it's always different. So the beauty of these pipelines, and this is where some of you might go, Dave, why did you not just show us this initially? Well, because you have to struggle a little bit to appreciate nice things. To fit, tune, train, cross-validate, whatever we want to call it, any model with caret, it all uses the same function, which is called train. So what do we want to do? We want to train a model. How do we want to do it? By cross-validating it. It's all inside this function here. So we should probably have a look at the documentation of this function. This one here, except you can't see it, so I need to move myself up here. Fit predictive models over different tuning parameters. Oh, great. So we can even specify which possible tuning parameters. Okay, so, right. So we probably need to read this at some point. I'm going to try to get away with just using what I know, but I want to mention the documentation. Furthermore, I want to mention that this is the real documentation. It's an entire book about the package. I think this chapter 5. So this book is sort of arranged in terms of like the order in which you have to think about things for doing the pipeline. We're focusing right here right now. So we want to train and tune our models. And this sort of walks you through doing that. But I'm going to try to do it. Well, I'm going to try to do it without reading the documentation. And if I'm being honest, I haven't done this since last semester. I've done it many times, but I haven't done it since last semester. I just haven't had reason to do it. So let's see if I can sort of scrape the rust off and get these models fit and tuned. Okay. And let's see if autocomplete helps me at all. It doesn't help much. Okay, so one thing you might notice here is there's these different usages, and depending on what you supply, you're using a different usage. We're using this formula method. Well, at least I want to. So I want to say this is our response variable. And I think we said everything else is cool as a feature variable. We're okay with that. So one thing right off the bat, which is really important. If this variable is a factor, train says, I am doing classification. If this variable is numeric, even if it's just a 0 and just a 1, train will say, I'm doing regression. So very important to be aware of that. I think it'll warn you if you like have only a 0 and 1 and say like, hey, do you want to do classification? Because right now you're doing regression, but something to be aware of. Okay, so the data is going to be the full training data. Oh, this is the form. I normally don't name this argument, but let's do it. See if it'll help with the autocomplete. Okay. So unfortunately, it doesn't really autocomplete. So these are the things I need to do. Okay. Maybe let's do it like this. Okay, so we have our formula, which tells us here's the response, here's what are the features. We have the data argument, which tells us, well, here's where those variables live, and here's the data to use. The next thing we need to tell it is the method that we want to do. I don't know if that's actually the next thing we want to do, but I'm going to do that next. So I want to fit a decision tree. So one of the tricky parts with caret is that the developers have said, okay, there's all these R packages for fitting all these different methods, but we want to roll them all into our package. So if we go here, there's this available models page. And if I search for tree, there's all these different ways of fitting trees. And in particular, I want to fit, I want to use the rpart package though, internally. So, okay, cool. This to me says, so the method that I need to say is rpart. Okay, cool. So if I put method rpart here, that's going to use rpart under the hood, in particular to the decision trees that are used by rpart. And it tells us, hey, there's one tuning parameter. It's called CP. Cool. Great. Okay. So don't need to deal with that. So this pre-process here, this is how we will pre-process the data. That is perhaps the next video. Okay. So this train control, this is sort of a really important argument. And actually, let's read the details of it. Okay. Train control. A list of values that define how this function acts. See train control. Okay. So the deal is, if we look at train control, the function. So train control is a function. TR control is an argument to train. So notice if I run this function, it outputs a list with all this information here. So what this argument expects is a list that was created from this function. I mean, I suppose you could do it some other way, but using this function will be sort of important here. So what this ultimately does is it says, well, how do you want to do the training? And that is like, how are you going to do resampling in order to, split up the data again, fit the model, and evaluate it? So let's look here. Method. So the possible methods are boot 632, optimism boot all, CV. Aha, we want to do CV for cross-validation. And then what's next? Number fold. Let's do 5-fold. And then there's a bunch of other options here, which we might return to. But for now, I think I can get away with doing just this. But so now it creates this whole list for me. But importantly, the method is CV, the number is 5. So what this is, I'm going to call this CV underscore 5. So basically what this means is this is the setup, and if I put it here, what this expression says now is I want to train a model where this variable is the response, all the other variables should be used as features, using this data, using decision trees from the rpart package, and using 5-fold cross-validation. Technically, a bunch of other stuff is encoded in here too, but we're just going to say it's giving us 5-fold cross-validation. Well, that's neat. Let's try it. Let's call this heart disease tree mod. Okay, and then I want to do like that. Okay, cool. Did I run this? Let's run this. Okay. Will this work? I hope so. Oh boy. This could be tricky to debug. I don't think I've ever seen this error before. Num in class non-numeric argument to binary operator. Let's try this. So I'm gonna try something real quick. Okay, that's interesting. So it's something with my bootstrap. Method CV number. Other examples of this down here. What happens if I just do? Oh. Okay, that makes more sense. Okay. Whew. Had me worried. We did it. But what did we do? Let's have a look. So first things first, let's see what we have here. Okay, great. So this tells us what we did. Okay, so the method we used is cart. Cart is an algorithm for fitting decision trees, which rpart uses. We used 525 observations in the training data set that we supplied this function. 11 predictors, features, 5 classes in the response variable. So these are the different levels of the factor that is the response variable. We did not do any pre-processing. We'll come back to that. We did perform resampling, in particular 5-fold cross-validation. Here it shows us the sizes of those folds. I'm genuinely curious why they're not all 420 and why this one's 421 and this one's 419. But I don't care because it's one observation. I don't care. Okay, so now it's saying, okay, well, here are the results. So it automatically, I didn't tell it this, it tried these 3 values for CP, which is the tuning parameter. Remember that sort of defines like if you're allowed to continue to split based on the improvement that you make. And it looks like, let's see, this is the highest accuracy that we get in doing so, which it actually tells us here. So it says accuracy was used to select the optimal model using the largest value, because that's what you do with accuracy. So it's by default using accuracy as the metric that we care about. And it's saying, with accuracy, you pick the largest. There are ways to do the 1 SE rule here. Maybe we'll attempt to do, let's make a note of that. Do 1 SE rule in caret. I probably said some other things that we're going to do, but I forgot what they were. Okay. So kappa is just another statistic that was calculated on the resamples. We're not interested because we don't even know what that is at this moment, but that's fine. So it says the final value used for the model was CP equals this. Okay, cool. But hopefully something that we've learned in this class is that what is printed out here is not really what's stored here. And I think if you've been following along, you're probably suspecting, wait, HD tree. Every now and again, autocomplete. It's a list. Ooh, look at all this stuff in here that we can look at. Method, our part. Okay, cool. We knew that. We told it that. Model info. Boy, I don't even know what this is. What else? What else? Model type. Classification. Okay, because again, remember, it figured that out based on the fact that we gave it a categorical response. What else do we have here? Results. Okay, that's interesting. So this tells us a little bit more than if we just do this. In particular, in addition to the accuracy itself, it shows us the standard deviation. Because remember, these were, this is the average of 5 different accuracies, and this is the standard deviation of those 5 accuracies. Okay, cool. And that was stored in the results data frame inside of this list. What else do we got? Pred. All right, that's nothing. Okay. Best tune. Okay, so this said, so we're using accuracy as our metric. We want the biggest one, not necessarily the one within 1 standard error. So this is the value of the tuning parameter that accomplishes that. Okay, cool. What else we got? I'm going to sort of skip around. Metric, accuracy. Again, that's a default. We can mess with that later. Oh, let's take a note of that. Use different metric in caret. Okay, cool. Where was I? I looked at metric control. Okay, final model. This is interesting. So, bit of my T for emphasis here. One of the best things about caret, in my opinion. Well, this is a precursor to the best thing. So essentially what caret did was it did 5-fold cross-validation for decision trees. It tried these 3 values for the tuning parameter. It determined that this one was the best. And then it did one more thing that's really nice. It said, okay, that's the best model of the ones that I'm trying right now. Well, then what I'm going to do is I'm going to fit it to the whole training data. So what is stored right here is exactly that. It's a decision tree model fit via our part to the entire training data with this value of the tuning parameter. That's super nice. But we'll come back to that in a second. Okay. Oh yeah, so this is actually I'm not exactly sure what this is, but this is details about how the resampling worked. Though I'm not sure for which value the tuning parameter is. Well, maybe. Oh, I think that's only for the best one. Yeah, so I bet if I average these, I think this value is exactly this value. Okay, right. So what this is this is the accuracy for the first fold of the best tuning parameter. This is the accuracy of the second fold for the best tuning parameter, so on and so forth. I think there's a way to modify calling train to get this for all of the tuning parameter values, but by default it only shows you for the best. Okay, what else do we have in here? Nothing that I'm super interested in. Okay, cool. Oh, okay, so what do we need to do next? So I didn't tell it what values of CP to try. What if I want to specify values? So there's two ways to do that. There's the lazy way, and then there's the not lazy way. Let's do the lazy way. I think that's the name of it. Let's check this. Tune length. Okay, so I could say, I want you to try 10 different values of CP. Let's do that. I should probably be setting a C before I do this. Okay, so this time it tried 10 different values. It turns out that this one was best. Let's just see here, highest accuracy. Okay, cool. So that's one way to do it. You could just say, well, I don't want to specify the exact values of CP to attempt, but I'll tell you how many to try. Okay. The other thing you could do instead of a tune length is provide a tune grid. What is a tune grid? A data frame with possible tuning values. The columns are named the same as the tuning parameters. Use get model info to get a list of tuning parameters for each model, or see this. Well, you know what? I've never done that. Let's try that. Get model info. I assume I have to do something like this. Oh, okay. Where does this start? There's a lot of information here. Okay, this is... Oh, gosh. Okay, well, that would be one way to do it. I don't like this. The other way to do it is to come back here and find the method you're using, and it'll tell you the tuning parameters. Okay, great. So I want to make a data frame that has one variable, which is CP, and a list of possible values to try for it. So let's do something like this. Okay. So if I run this, it's a data frame, like we said. I want to get in the habit, though, of not using data frame. So let's say that min split was also one of the parameters. It's just not the way they implemented it, but let's say it was for a second, right? So let's say I did min split, right? So 1 or 2, 2, 2, 2, 2, 2. Okay. So now I have a data frame with the names of the two parameters and the values to try, right? But like, let's say I wanted to do these values of CP for like 3 different values of min split, right? So instead of data frame, I'm going to use expand dot grid, and let's do this. So I want to try min split of 2, 10, and 20. For min split of 2, all the values of CP. For a min split of 10, all the values of CP. For a min split of 20, all the values of CP. So we don't actually need this right now. But what I'm saying is, instead of ever using data frame to create the data frame, just get in the habit of using expand grid. So this is going to go up here. We'll call this heart disease tree tune, not rune, tune. Instead of tune length, we'll do tune grid, and we'll supply this here. Let's run all this. And now we see that it tried the values of CP that I asked for. Note that these aren't actually as good as the ones that tried by default. So I will say that using tune length instead of grid, the authors of the packages have sort of generally looked into what are reasonable things to try for the values of the tuning parameter. So often you'll get something that's like reasonable unless you're in some sort of like weird edge case for some reason, but something to try. Okay. Let's actually revert to that tune length. Let's make it 10. Okay. So, all right. So I have accomplished this. Oh, let's fit this real quick now that I went backwards. Okay. So I said that I want to do k nearest neighbors as well. I'm going to try to make this as easy as possible. Wow, wasn't that easy? I literally changed just this. So this is using what we're familiar with, KNN3 under the hood. So let's look at that real quick, right? So we're using KNN. Technically, it doesn't use any libraries because KNN3 is part of Caret. That's why it says that. It has one tuning parameter, K. Wonderful, great, grand. And these are the results. And so K is 23, gives our best result, which is here, which is not as good as the tree. And we could do things like expand the tune length here, or we could do something like, let's specify a tuning grid here. Let's do, so we said that K is the tuning parameter. Let's do, I don't know, this is silly, and it might take a second to run, but let's try everything from 1 to 100. Okay, so I need to set this to tune grid, and I called it this. I forget if I ran this, so let's do it. And then let's run this. That might take a second, because I'm trying a lot of different models. That wasn't too bad. Aha, and now we see that it tried all values of K from 1 to 100. The bottom here, 26 was best, which gives us this, which I don't think was as good as what we got with a tree. Okay, so now I said I wanted to do a boosted model. I haven't really talked about boosting yet in this class. I still need to, but I want to prove that we can do it and determine if it's working better than the two other models we just tried. So let's go over here and search for, I just realized that I'm covering up the search bar with my ugly face. So I'm searching for boost. Okay, I kind of know what I'm looking for, but okay, so kind of one of the first boosting methods you generally see is this GBM. And it has 1, 2, 3, 4 possible tuning parameter values. So notice that the method is called GBM. It may ask us to load that package, but we're going to ignore that for now and just go with the flow. So what I want to try to do is just swap GBM in here. We'll call this GBM, this gradient boosting machine. I want to go back to using a tune length. Actually, you know what? I don't want to specify either tune length or tune grid. I want Caret to just pick it for me. I'm going to let Caret do its thing. It'll hopefully come up with some reasonable answers. I have no idea how long this is going to take to run. Oh, okay. So it's spitting out a bunch of information along the way. Actually, so one thing you can do, so under the hood, it's calling this GBM function. So any of the arguments here, we can pass. This verbose argument here is the one that spits out all this stuff. If I set verbose to be false, it doesn't print out all that stuff when I do the tuning. All right, let's look at the results. Ooh, okay. So it tuned over 2 of the possible tuning parameters. So let's read this here. Tuning parameter shrinkage, which is one of the 4, was held constant at a value of 0.1. That's why it's not in this table. Tuning parameter n min obs in node was held constant at a value of 10, which is why it's not in here. Can I? No, okay. Accuracy was used to select the optimal model. Okay, we haven't told anything else. The final values for the model were n trees equal 50. Interaction depth is 1. Okay, so this was the best model here. So an accuracy of 0.628, which I believe, based on our previous results, is our best model yet. But so the thing I want to do now, sorry, I guess I'm in my eye, is I want to go back to, I want to specify the values of the tuning parameters for this one once. So let's do this. So GBM. So there were what? There were 4 tuning parameter values. So I need to specify values for all of these. Okay. So let's do this. Okay, and I want to sort of do it I just want to expand what we've already tried here. So n trees, I think I can just specify 1 value for this. We'll see what happens with that. Because I think if you try 200, it automatically tries lower ones because it's growing more trees along the way. I can't really explain that without getting into the details of boosting, but we'll just try it. Okay, interaction depth. It looks like we tried 1, 2, and 3. I'm going to continue that. Okay, so shrinkage, it only tried 1 value, which was 0.1. So let's try 2 values. Let's try 0.1 and 0.5. And then n min obs and node, it only tried 10. So let's try smaller values. Let's try 5 and 10. So by doing expand.grid, we see we get this whole grid. And I think this is what I need, but if it doesn't do the trees correctly, I'm going to come back and change it. But so what I want to do is I want to add tune grid is this thing here. This might take a second to run because it's more models it has to deal with. I have no idea how long this is going to take. For all I know, it's going to take an hour. Ooh. That's interesting. Okay, so it didn't run. Let's try... Okay, let's do this. Let's try to go with just the values that it initially had and see if that works. And then we'll go back and expand it if I actually get it to work. It's always dangerous doing this without doing it first, but I think it's more instructive for me to screw up a bunch. Oh, that one ran. But I want to see if it did what I thought. Oh, no, it didn't. Okay, so to replicate the default behavior, I need to do... So what was it? 50, 100, 150. Let's just try adding 200. I think they may have changed how that worked. Okay, that ran. Okay, so now we see some expanded results. Ooh, that actually helped. Wait, no, did it not? Oh, this one's even better. I should really be setting a seed before I do this, but bottom line is this is definitely working better than a single tree, which kind of makes sense. Okay, so I also wanted to do, let's just do like 0.3 here, and let's try like 5 here. I hope this works. I don't know why we would have gotten that error previously. But basically, the whole point is I want to expand the possibilities of this. So basically, like, you know, at the end of the day, I just need to get the analysis done. Arguments apply different number of rows? Let's keep this constant as 10. I have a feeling for some reason it's that parameter, but I can't think of why. Okay, that ran. Boosting can be a little tricky sometimes. Okay, so notice I just tried a bunch more things, right? So if I have all the time in the world, I just want to try a huge tuning grids to try to find like a good set of parameters. But you might notice that like even with the expanded tuning grid, we're not seeing like wildly different results. It looks like the best result is here. So it's probably not worth it to expand it all that much. You know what? Let's do one more model while we're at it. My favorite model. So I'm fitting a random forest. Something else we still need to talk about. That worked pretty well. About as good as the boosting, which is to be expected. So I'm thinking. Something I need to talk about at some point is this notion that we have a ton of different models we can try. Me, personally, I'm going to suggest you always try 2. And within those 2, one of them will probably work good. A random forest and a linear model. I need to explain that position more so, and I'm going to reference a few papers that sort of argue this point. But random forest is like my go-to model. If I want just a black box model that can take input and make predictions, unless I'm dealing with like image data or some truly huge data where like deep learning would work, give me a random forest. If it's tabular data with like not big data number of rows, not big data number of columns, I just want to do a random forest. But anyway, so I think what I want to do now is kind of summarize something about what we've done here. Wait. Oh, wait. Didn't I fit? I could have sworn I fit K nearest neighbors. Well, it won't be hard to get it back. Did I? I could have sworn I had fit K nearest neighbors. Anyway, well, let's do this. Because it's so easy. I don't know why I did 100, but I did 100. Okay, so I also fit K nearest neighbors. I kind of don't actually care about the results. Okay, so tree model. Ultimately, this is the tuning parameter that we picked. And again, so the tree model went back and fit the model with this value of the tuning parameter to the whole training data. With K nearest neighbors, with this most recent run that I did, it selected K is 83. Where's 8? Oh, that's funny. 83. Okay, not that great. But again, it took that model and it fit it to the whole training data. Here's what we picked for a boosting model. Here's what we picked for random forest. Here's the cool thing. Okay, so let's say I want to call predict on these things. Because I don't want to look at the test data yet, I'm just going to make predictions on the whole training data. Normally we wouldn't care about this, but I want to do it. Huh. So the huh there is because we used 4 different model types. The way predict works on all of them, because they were all fit via the train function from caret, it always works the same. So there's actually another argument. It's type equals class, right? So I'm going to put this everywhere and run those again. So obviously the results are different. Wait, oh, sorry, it's raw. Hey, at least it's a good error message. So the results are different. They're actually pretty different, it looks like, but I don't care about that right now. What I care about is the way to obtain them was the same. And remember, so what predict is doing is it's saying like, oh, hey, there's a lot of stuff stored in here. But remember, there's this final model thing inside of here. It's reaching down in and saying, well, yeah, I'm going to make predictions based on the model you picked and then refit to the whole training data. So it's sort of abstracting that whole process away from us. Okay, cool. But isn't that nice? So if I change raw to prob, it gives me, so for the first observation in the training data set, here's the probabilities that it is the various possible classes. So the takeaway here is that if you fit your model with train, no matter what type of model it is, the predict function works the same way. This is where I need to like be on the lookout, because I think you're all gonna be mad at me. Because you're like, oh, Dave, we spent so much time dealing with predict not working the way we think this semester, and now you're showing us this? Two things. One, the struggle that you experienced makes this all the sweeter. But two, in my opinion, that struggle was useful because it helped you think about R a lot more and searching documentation, reading error messages, and all that. But because if I just jumped to doing this, you wouldn't have experienced any of that. You wouldn't have learned as much. Okay. But so that's really great. So like, let's say that of these models, this one was the best, right? No, I don't want to do this. I was about to calculate a test accuracy, but I don't want to look at the test data yet because that's going to influence my thinking. But okay, so what do we have left to do, right? So now we kind of have, so beautifully, this we realize now is all taken care of in Caret, right? So this we use to create data partition function and then do the usual splitting. To do this, we use the train function. This happens automatically as a function of using train. This is very easy to do. You just say predict the model that you fit with train, data equals test data. There you go. And you don't have to worry about how predict works because it's always either going to be raw or prob, depending on what you want. Okay, so I guess what's left to do is sort of two things. This here, which is like dive inside of the cross-validation and be like, how should we be dealing with missing data? Should we be processing the data in different ways? Things like that. And given where the clock is, I'm going to save that for next video. But then the other thing is, everything I did in this video was sort of a process thing, but I wasn't thinking about the bigger analysis, right? So I was just, I mean, these were just numbers and classes to me. But remember, these classes have meaning. So once we take care of some of this, which will be influenced by the context here, then we need to go back and start thinking about what it is we're trying to do. And something that might come into play with that is this here, right? So is accuracy really the metric that we care about? I'm probably going to argue no, but that's sort of where we'll go next time. But yeah, so bottom line is the takeaway from this video, in my opinion, was that the Caret package exists. Now, I don't expect you to read this whole book, but I think it's important that you know it exists because as you use Caret, you'll want to reference certain things from here. Perhaps reading just this chapter here, chapter 5, it'll sort of go through a lot of the things that I just did, but in more detail. And I'm going to do it again next video too, so we'll get into some more of this. Yeah, hey, we talked about a lot of this. But I wanted you to know that this exists. But also, maybe you're like, I don't like this Caret thing. It seems weird. I don't know. Maybe it just doesn't sync with you. There are these other alternatives. I'm not as familiar with them, but I might try to do one of these analyses in one of these other systems within R. But yeah, I'm just familiar with Caret, and it gets the job done. Okay, so I went a lot longer than I thought I was going to in this video. But anyway, if you made it to the end of the video, good job, and I hope I'll see you in the next one.